So what's our next step? Our next step is really to look at how the electromagnetic fields transform under Lorentz transformation. Okay, so how are we going to go about this? Well, we're going to do it piece by piece. So let's imagine that we have motion at a certain velocity in the direction x. Okay, and let's imagine that we want a simple situation where we've got some electric field, say pointing perpendicular to the motion like this. So this would be our E field. Now, how would we construct such an E field? Well, we would really put parallel plate capacitor in the system, yeah, like this. And let's imagine that my plates are infinite, and I put some surface charge density on these two plates here. And if I want the field to point up, I would like to have a certain surface charge density plus sigma 0 on the bottom plate, on the bottom plate, and minus sigma 0 on the top plate. So then the E field for this, let's call it E0. This E0 would be equal to just, as usual, sigma 0 over epsilon 0 in this y direction here. Okay, so that would be the thing. And I imagine that my capacitor is extended absolutely everywhere, right? So it's just infinite in both directions like this. And I'm looking at a particle moving inside the space between the plates with a certain velocity vector here. So let's say that say that particle moves at velocity. So moves at velocity v0. Then the surface charges, the surface charge it measures, or it sees, I should say, would be equal to the following thing. It would be the original surface charge sigma 0 that we have here, but because I'm moving at a certain velocity v0, there's going to be Lorentz contraction in this direction here. And if I've got a uniformly charged plate and I contract it in any direction whatsoever, I still get a uniformly charged plate, but with a charge density that has increased by the contraction factor. So essentially now the new sigma that the particle sees is corrected by this gamma 0, where gamma 0 is just the factor associated to moving with velocity v0. Okay, so I've got this this relationship here. Now the moving particle here, once again, because this whole thing, if you want, would be completely rotationally invariant if I were to rotate, say, around the y-axis on this, the only field that the particle can see is along the y-axis as well, in the moving frame of the particle. So that means that the electrical field seen by the particle is now, again given by Gauss's law, but with this corrected surface charge density, so sigma over epsilon 0, but now again along the y-axis. Okay. If I were to do that, you know, I can rotate this whole construction along the y-axis and it doesn't change at all. So really, I can promote that relationship here into a relationship relating the perpendicular to the motion components of the electric field. Okay? So the conclusion is that the electric field perpendicular to the motion of the test particle that we have is simply corrected by a factor gamma 0 as compared to the one in, you know, what we can call the lab frame. Okay? So the original frame in which we measured the surface density sigma 0. So that's the first part. Now you see, so that gives us an idea about the way fields transform perpendicular to the motion, but we now need to know how the field transform parallel to the motion. But to do that, essentially what we do is we come back here and we imagine the particle moving in the y direction. And of course there would be, again, contraction in the y direction. But as you remember, the electrical field between a parallel plate capacitor, between the plates of a parallel plate capacitor, does not depend on position. It's the same everywhere. So that means that we've just proven that the parallel part to the motion stays the same, because contraction only affects directions along the motion, and that doesn't change the surface charge density, so the thing is the same. Okay, so that's the transformation rule for electric fields that we have in this simple situation here. Now, there's of course one issue. Okay, so let's not forget that in the moving frame of the particle, okay. So in the moving frame, the plates, they carry a current, right? Because we imagine that in the lab frame, there was no current in the plates, but if I start moving, then it's as if I was stationary, but the plates were flying by me at velocity minus v0. So that means that there is a surface current density that shows up, okay? And the surface current density, so surface, or the surface current, let's call it. So this K, now let's do it for the top plate. What would that be? So it would be a plate with surface charge density minus sigma 0 moving at velocity minus v0. Okay, so so essentially, and again, because of the Lorentz contraction, the sigma 0 becomes a sigma. So what the particle sees is a current, sigma v0, now in the x hat direction, right? In its direction of motion, because so that's from the top plate, right? So you just have this negative charges moving left is like a positive current going up. So that's why you have that here. And on the bottom plate, there would be the same thing, but with a minus sign. Okay. So again, from Ampere's law, we can determine what the magnetic field is. So what we would have is that the magnetic field would vanish outside of the construction. It would be non-vanishing only within the construction. To compute it, we just construct an Amperian loop straddling the surface here, going up and down. On the outside, there's nothing. On the inside, there would be a line integral capturing the surface current. So we've done those exercises before. What you'll find is that the magnetic field associated to this current inside the parallel plate capacitor is just minus mu 0 sigma v0, and this is aligned along the z-axis. Okay, so if you want, the magnetic field is going like that way. Okay, just by the right-hand rule, you can see that. Okay, so so that's one thing. Now, say we have yet one more frame of reference. And this frame, let it be S bar. It's moving at velocity v bar, okay, with respect to the original one. Well, I mean, it's the same thing, so we can just use the same equations and see what we get. what we'd have is that in that particular frame, there would be a Y electric field given by sigma bar over epsilon 0. There would be a BZ, which would be equal to minus mu 0 sigma bar V bar. Okay, the same formulas as we've just seen, except that now, of course, we would have a different thing. So the sigma bar would be equal to gamma bar sigma, where this gamma bar is just the other contraction factor, minus V bar squared over C squared square root. Okay. And the V bar could be seen as an addition of two things. So it could be adding a velocity v to the one moving with v0, 1 plus v0 over c squared. Okay. So now the challenge is to express E bar and B bar in terms of things only in the original moving frame. Yeah, so E and B, and with data for that frame. So then we'd like to put the velocity v associated to that. Okay. So how do we go about doing that? Well, so first of all, we can just compare the things that we have. So to start, we can just see that the EY is going to have a ratio of gammas like this, and the B similarly would have gamma bar over gamma 0, mu 0 sigma V bar. Okay, so if we look at this this factor here, if we look at this factor of gamma bar over gamma 0, we can just work it out explicitly. So square root of this with then the square root of 1 minus V bar over C squared. And now I can just make use of the relationship that I have between the velocities here. So what do I want to do? I'll just multiply by C everywhere here to put the 1 over C bars into something simple. So in the numerator here, C0 squared minus V0 squared. Okay, and now if I look at this, you see I've got V plus V0, then this denominator here, there's a square. So this denominator I'm going to multiply out everywhere. So there's going to be a 1 plus V0 over C squared here. And now in the denominator, I'm going to have, again, the C squared. But now I've multiplied by this thing, so I'm going to have this thing squared. 1 plus V0 over C squared. All of that squared. Minus the V plus V0, all of that squared, and then all of this in a square root. All right, so you see what happens in this case here. I've got C squared that stays. I've got 1 plus 2 times VV0 plus this thing squared. And then I've got the V squared, V0 squared, 2VV0. So the 2VV0 term here is going to cancel against also the cross term here. So then that means that I just have like the difference of the sum of two squares right? And you know how to rewrite that. So so here it's going to factorize out some c squared minus v0 squared, and it's going to leave me a c squared minus v squared. Okay, so then the c squared minus v0 squared falls against this one, leaving just the c squared minus v squared. So in total, just get that this thing is 1 plus v0 over c squared divided by, I mean, redividing again by the 1 over c squared because of the, it's here. So 1 minus v squared over c squared, and then square root. Okay, and this is just recognizing my gamma. It's gamma times 1 plus v0 over c squared. Okay, so that's the first step. Then what we can do is just rewrite this equation here. So it allows us to rewrite this e bar y as being equal to gamma 1 plus v0 over c squared, okay, times sigma over epsilon 0. And now I can just recognize my my equations, because I had my b here, which was also mu 0 sigma v0. So I'll want to replace this thing here by the b, and you see there's a minus sign, mu 0 sigma v0. Okay, so so I've got some mu 0 epsilon 0 showing up here. This whole thing I can just have gamma, so sigma over epsilon 0 is just EY. And now if I do v0 over c squared sigma over epsilon 0, so I'll just have v times the magnetic field over mu 0 with a leftover epsilon 0 at the bottom. So that means just v times bz divided by the epsilon 0, and then I had the mu 0, and I've got the c squared hanging from this. Okay, but of course you recognize, so epsilon 0 mu 0 is 1 over c squared, so this thing trivializes. So this whole thing just becomes gamma ey minus v b z. Okay, so now we can do the same construction just by a rotation. Just imagine taking our whole construction here. We had our plates in the xz plane, but now I could imagine just rotating them in the y-plane. So I take a rotation along the x-axis, and I do like a pi rotation from the top clockwise into this. So I transform my axes. So y becomes, where I got it, y becomes minus z, and z becomes y. Okay, so I can just rotate these results here and obtain a similar thing. Maybe maybe you see what I mean. So what I would just get is that I would just change the relationships, and that would give me that e bar z is equal to gamma times ez plus v by by this rotation I just talked about. Okay, so for the electric field, that's the thing. For the magnetic field, I could do the same kind of logic here. So again, going back to this expression here, I would again substitute the value of this ratio of gammas that we had. So we can do that maybe quickly. So the bz, b bar z, is just minus gamma with 1 plus v0 over c squared. And now I've got the mu 0 sigma, but then the v bar, right? So this v bar, and this v bar I want to get from here. So I will substitute that in here. V bar is just v plus v0 divided by 1 plus v0 over c squared. So you see this is quite friendly because a lot of stuff just falls away straight. And I can immediately identify that this is gamma times the bz, okay, minus epsilon 0 mu 0 v e y, right? Where again I've substituted for sigma with this and for v0 from the b, okay. So this term, right? So the v0 gamma gives the b, and then the other term here coming from this gives the epsilon y. Okay, and this is just gamma times bz minus v over c squared e y. So again, this one I can rotate to get the other component of the magnetic field. So the z will become y, and y will become minus z in the axes for the electric and magnetic. So that would mean that my by would be equal to a factor of gamma times by, now plus, because the y becomes minus z, v over c squared e z. Okay, so so these are for the components of the electric and magnetic fields perpendicular to the motion that we have, right? So we now know how these perpendicular components transform. Now we just need to have the components parallel to the motion. Okay, so for the parallel components, so we already know that the parallel electric fields is the same. So therefore, E bar x is equal to E bar, E bar x is equal to EX. Okay, so for BX, we have to play a different game. So we imagine that that there is a solenoid in the original frame. So the solenoid will generate magnetic field along the x direction, okay? And the particle is moving inside the solenoid, and the magnetic field inside the solenoid is independent of the position inside the solenoid. So, so essentially, you remember that the magnetic field is proportional to the current in there times the number of windings. So the windings which were n in the original frame, because of Lorentz contraction, they become tighter by this factor gamma in moving frame, in the moving frame. Okay? But the clocks in moving frame, they move slower by time dilation. So if I look at the current in the moving frame, it's going to be slowed down by a factor 1 over gamma as compared to the current in the original frame. Okay? Now that means that the product is unchanged. Okay? So the magnetic field is also unchanged, longitudinal to the motion. So that gives us, in summary, the following transformation rule. So for motion along the x-axis, we have the following transformation rules. So the x components of the field are unchanged. The y component gets a blend between, sorry, that's a gamma. It gets a blend between the electric and the magnetic field of the original frame. And the same thing with the z component. For the magnetic fields, the longitudinal component is unchanged. And once again, the transverse components become a mixture between the electric and magnetic fields of the original frame. Okay, so these are the general laws for motion along x. And if you get motion along a different axis, you need to do a more general transformation. But if you choose your axes correctly, you can use the transformation that we just saw here. So there are two little cases that are a bit easier. So the first one is if I put the magnetic field is equal to 0 in the original frame. So that means that the B bar is equal to gamma times V over C squared with EZ along Y, right? Minus EY along Z. Because of the relationship between the fields, I can reabsorb this factor of gamma. So it gives me V over C squared, and rewrite them in terms of the new frame, EZY minus EY Z. Okay? So what this means is that the new magnetic field is minus 1 over C squared V crossed into E bar. Okay, so that gives you a relationship between the electric and magnetic field in the new frame. The second easy case that's useful for some applications and problems is if the electric field is equal to 0 in the original frame. So in that case, the electric field E bar is going to be minus gamma times V times BZ y hat minus BY Z hat. And again, by the same logic, it's just minus V times B bar Z y hat minus B bar Y Z hat. So what you get is that the electric field is just V cross B. Okay, so these are quite handy little equations that that can prove their usefulness in some problems that you